This is Julia. I'm going to be working through Week 10's lab slides, which are on linked lists. So let's get started. So a couple of announcements. We have released our mid-semester survey, so you can receive extra credit for filling it out if you, so just a reminder, if you haven't filled it out already, please do so because we do read all the feedback and make sure we're doing okay in the class with supporting students, and we always try to take suggestions if you have any. So if you have anything you would like us to know about the course, please do with the mid-semester survey. And the MAPS deadline, as you might know from Piazza, it was changed a while back, but it's going to be due this week, Saturday, April 4th at midnight. And that's PST, so that's like regular time in Berkeley. And now we also have 2 more slip days, so you have a total of 5 slip days in the entire class to use on homeworks and projects. Okay. So moving on to the actual material of the lab, we're going to be talking about linked lists, which are a data structure that you'll probably learn more about in the future, especially if you take 61B, because it's a really common data structure in computer science, and I feel it's a really natural extension of regular lists in Python. It's just that they have this special characteristic that we're going to talk about. So basically, linked lists are just another way to store data. So we've used like Python lists and dictionaries and all sorts of things like tuples, and basically this is just another way of storing data. But it's more efficient in some cases. We'll talk about how inserting and deleting can be a lot faster with linked lists. I'll just briefly mention it, but you don't really have to know all the details, since this is going to be like an introduction to linked lists. So we'll just try to teach you like the recursive part of it, and we're basically trying to get you to understand linked lists in the sense of recursion as well as OOP, which is object-oriented programming. Alright, so breaking down linked lists. So we typically draw linked lists or any kind of link in linked lists like this with a box that contains 2 smaller boxes inside. And the reason for that is because every link has 2 components. So it has a link dot first. Oops. Just need to charge my pencil a little bit. Okay. So it has a link dot first and a link dot rest. So here is the link dot first of this one, and it's going to be the value that's stored in that link. So the link stores its own value and then has a second box to point to the next value, and that's how we connect them. So the second box is really important for connection, and this is called link dot rest. And I'm saying link dot rest with a capital L because we're talking about the class. But if it's a particular link, for example, this link is actually called lnk, then it would be link or lnk.rest. So it's whatever link and then .rest because we're talking about the attribute of this particular link. Okay, so links can also be empty, and that means we think of it as just like a link with no value. But we need to have some kind of thing that represents empty, because at the end of the list, we need to indicate somehow that we've ended the list. So link.empty here, and you'll see this in the implementation of the code, is just an empty tuple like this. So it's like empty parentheses, but as a data type, this is an empty tuple. So if you ever get like some kind of error that says like tuple does not have attribute first or something like that, it's probably because you're returning link.empty at some point. Okay, so we covered the empty part, and we've covered how links have a first value called link.first and a pointer to the rest of the linked list. And it's really important that we have this pointer, because let's say this pointer was just deleted. Well, then we just have a link of 7, and all of the 9, 3, and the link.empty is gone. So that's how we connect them together. And if you're wondering how this plays in with like regular Python lists, well, you can kind of think of it as like in Python, all of this has been abstracted away from you. For example, I don't know the particular implementation, but perhaps like Python lists are actually linked lists in the source code or something like that. But when you use them, or when I use them, it's just a regular list where like everything is done automatically. So I don't have to worry about the .rest, .first, or anything like that. But here we're going down into the details to actually understand this for ourselves. So although we might just like want to use a regular list, it's good to understand this and learn the cool tricks behind it. Okay, so breaking down linked lists further, linked lists can store any data type, numbers, strings, and even other linked lists. So you might start to see the recursion here. So here we have a string, and this is the value of that link, and another string, other things. You could put basically anything, including other links. And so talking more about the recursion behind linked lists, you'll see that this is referred to as link.rest. So it's kind of confusing sometimes for students, because when we call things link.rest, it points to the next link, but sometimes we use link.rest to refer to the pointer. So basically we're just saying that link.rest is a pointer to the next link, and that's how we connect them. So when you call link.rest, it's actually referring to the next link, which is pointed to by this box over here. And then link.rest.first is going to be this value. I just highlighted over here. Oh, that is the same exact color. Alright, is that better? Cool. Link.rest.first is this value, and then you can keep calling .rest on it until you have like an empty link. So this is link.rest.rest, and basically the number of links that you want to move on to is the number of rests that you have to have. So you can start to see that linked lists are a recursive data structure, because somehow we're going to recurse on the rest pointers of each link. And notice that each link looks pretty much the same. It's just that the values are different. And when we have link.empty here, oh, by the way, this is just a shortcut to say that this is link.empty. But if it makes more sense to you, you can say that it points to like an empty tuple. So as I was saying, because we have this unique stopping condition, we know that when it points to empty tuple, you might want to think about like how this plays into our base cases for our recursion. Alright, how are linked lists implemented? So we're going to use a class for this, because every link is going to be an object, and we're going to take in two things. So first of all, it's the first value. Basically, the first value is just the value of that link. We're not referring to like any first link or anything like that. It just means that it's the first box inside the link, which is the value. So this is first, aka the value. Okay, and then we're going to set that to its attribute, and then we're going to set self.rest to whatever the rest is. And notice by default, rest could be empty. So basically, when we want to create a linked list such as this one, we have to nest our links, or nest our function calls, because when we create this link over here, so this part over here, just the link 17, is going to create this 17 link. But then we have to create its rest, which is just the rest of the link list. So we have to create 15. But then 15 has a rest, which is link 13, and then 13 has a rest, which is link 11, and then which has a link of 9, and then this 9 doesn't have anything because it's just empty. So, or sorry, it's not empty, but its rest is empty because it's the end of the list. So you're going to typically see links being made like this. And what you can do is try to start from the very inner and work your way outwards. Although I like to think of it as starting outwards from this end of it, and then trying to see what its rest is and see what that rest was. So basically, I think it's a more intuitive way of thinking about it because you're starting from the start and then trying to go to the end. Okay. So simple workflow, we have a couple of example questions here. So remember that when we define a new linked list, we can try to start from this end and make the links. So we're going to have this link of 2, and then it points to another link of 3, and then it points to another link of 4. And then because this 4 doesn't have anything further, it's just going to have link.empty as its rest. So that means it's the end of the linked list. And then the larger link is going to be the previous link as we defined before, and then it has link 1 in front of it. So basically we're just adding the value 1 in front of the list, and then that's how we get this. So remember, this is going to be your first, and then this is going to be the rest. Okay, and smaller link is going to be link.rest.rest. So we're going to follow the pointers. So this is, it's the smaller link. Okay, so it's going to start from link, and then follow the pointer. So this is 1 rest. Okay, and then that's another rest, so it points to the 4 link. So smaller link is just the 4 link, because we had 2 rests. Alright, so link.rest.rest first. Well, we know that's the 4 link. Remember that we're pointing to the link, not the value. We have to use dot first to get the value. So this is 4. And then larger link.rest first. So we're going to follow arrows. Larger link, and then its rest is the 2 link, and then dot first is going to be 2. So that's why we get 2. And smaller link.rest is just going to be link.empty, because it's just the 4 link, and the 4 is not connected to anything. It doesn't have a rest, but it's connected to the rest of the list, because 3 points to it. Okay, so we got that one. Alright, now we'll talk about removing from a linked list. So let's say we have this list 2, 3, and 4, and we want to remove the node with 3. So what we're going to do is going to set this pointer, which used to point to 3, to point to the value after it. And that's why we have this pointer over 3. So basically what it's just doing is saying that we no longer want to include 3, so we're going to point to the one that it was pointing to. And that way we're skipping over it, because it has no links to 3. So 3 is just like some, some floating box around there. Nobody's pointing to it, and stuff like that. And another point is that it's pointing to 4. So we don't actually have to remove the pointer to 4. 3 could be pointing to 4. But since we don't have any connection to 3 at all, like we don't have any handle on it, it just disappears. So that's how it's not included in our list anymore, because 2 no longer points to 3. So we don't have access to 3 anymore, even though it still points to 4.